Good evening. This is lecture number 26, the last lecture in module 4. We will be covering flexibility method in matrix analysis of structures with axial elements. So with this, the fifth lecture in this module will be complete. Flexibility method. Space trusses application of reduced stiffness method we have already covered in the last session. This is covered in the book Advanced Structural Analysis. So this is flexibility method. As you can see, we have already finished the two stiffness methods, the conventional stiffness method and the reduced stiffness method. Now we will see how we can apply the flexibility method, which is a little easy to understand now that you have done the reduced element stiffness method. So let us refresh our memory about transformations. We know that there is a flexibility matrix at the element level which relates the element level forces to the element level displacements. Similarly, at the structure level, you can relate the structure level forces to the structure level displacements. Usually in the flexibility method, we keep aside the reactions. There are ways of dealing with reactions, I will demonstrate in today's lecture as well. So that is why we refer to only the active coordinates. So the flexibility matrix F, when you pre-multiply to the force vector F, will give you the displacement vector D, right. So these are the two flexibility matrices, one is at the element level, the other is at the structure level. Then you have transformations from the global coordinates to the local coordinates. So the first transformation is the TF transformation. Remember, we had the TD transformation in displacement method. So here we are moving on the left side, you can convert the load vector to the element force vector through a matrix called the force transformation matrix, and the principle of contragradient, the contragradient principle tells us that TF transpose gives us a relationship that establishes compatibility, that simultaneously establishes compatibility from the displacements at the element level, you get the displacement at the structure level. We have done this in module 3, but we will refresh in this module as well. And this is the reason why in statically determinate structures you do not have to explicitly satisfy compatibility. It is automatically satisfied when you apply static equilibrium equations, and of course you have this diagonal which allows you to shift to the element deformations from the load vector directly. Please note that the TF matrix is a unique matrix, it is a square matrix for a statically determinate structure, and from the element flexibility matrix unassembled F star and the TF matrix you can generate the structure flexibility matrix in much the same way we did this in the stiffness method. Remember, we did TD transpose K star TD and we got the K matrix. Similarly, you are getting the F matrix in this fashion. Okay. You will understand best when we do an example. So let us do that. Let us take this example. This is a 5 bar truss or pin jointed frame. It is simply supported, so it is externally statically determinate, it is internally statically determinate. You can check M plus R is equal to 2J, and you are given some loads, two loads. One is a direct action of 100 kilonewton and the other is a lack of fit. Okay. So bar 4 is too short by 2.5 mm. Question is very clear, find out all the bar forces and the joint displacements. I mean, these are the unknowns in the structure. You can also get the support reactions very easily, right. So let us demonstrate how to apply the matrix method using the flexibility formulation for a very simple problem of this kind. How do we do this? Well, first you have to define the coordinates. Now we can identify 5 active coordinates. We have done this earlier if you recall for the same example. So 1, 2, 3, 4, 5, these are the 5 coordinates at the active degrees of freedom. And the input load data says that F3 alone is non-zero, F3 is 100 kilonewton, clear? The direction is in the same positive direction as the coordinate 3, F1 is 0, F2 is 0, F4 is 0 and F5 is 0. We are also told that there is an initial displacement, bar 4 is short by 2.5 millimeters, which can be written as minus 0.0025 meter, and that vector we refer to as the initial displacement vector at the element level. Is that clear? This is a symbol d star initial, and d1 star is 0, but only d4 star is non-zero, it is minus 0.0025. So you must be able to write down the input data in terms of the notations that we have developed for matrix method. Is this clear? Okay. Now just look carefully. Do you think these initial displacements will introduce any internal forces? No, because the structure is just rigid, the structure is statically determinate, the bar will be allowed to have the length it wants to have. If it is short by 2.5 mm, it will remain short by 2.5 mm. All the other members will retain the lengths that they have been manufactured with, and the joints will just move. So this is something that you know, that in just rigid statically determinate structures, if you have a lack of fit or a temperature change, it does not introduce any internal forces, it does not introduce any support reactions, it only affects the geometry. You will get joint displacements. Is it clear? That's how it works in a statically determinate structure. If it is indeterminate, and we are going to do that in the next problem, then there will be a tug of war, some members do not want to change their lengths while others want to, and there is a compromise and there are internal forces created. So even before you started the problem, you recognize that it is only the 100 kilonewton direct action that is going to give you any internal forces. That 100 kilonewton will give you joint displacements, certainly you will get d1, d2, d3, d4, d5, but the other load, the indirect load, will add on to the joint displacements, but it will not add on to the internal forces. So it is necessary to be good in structural analysis fundamentals and then use matrix methods only as a tool, otherwise you will not be able to appreciate the solutions that you get. As far as the local coordinates are concerned, you are dealing with exactly the same element that we dealt with in the reduced element stiffness method, right. You have only one internal deformation, and that is the elongation in the bar. You have an axial flexibility, which is the reciprocal of the axial stiffness, and it is called flexibility. Fi is equal to Li by Eai. Is it clear? And you have 5 bars, all the bars are prismatic, the bar areas are given, the lengths are known. It is a simple problem, the lengths are either 3 meter, 4 meter or 5 meter, the diagonal lengths are 5 meter. So actually you can compute the flexibility values, F1, F2, F3, F4, F5 can be easily worked out. Is it clear? And look at the units of flexibility, it can be either meter per kilonewton or millimeter per newton, it is the same, it works out to exactly the same. Is it clear? We are ready now to proceed. How do we solve this problem? Generate TF matrix first, then
Then F
then F star,
and find
F star into TF,
Then get the structure.
TF transpose, get F, then
Get the structure.
get the displacements dA, then no, you can get the you see that's the difference here. You can get the forces directly because there is no redundant here. So this after you get the TF matrix directly you can get the forces. Okay, so that's it. Very simple. First you find the TF matrix, then you write down the unassembled elements flexibility matrix. From the TF matrix itself directly you can get the bar forces in that step itself, then the structure flexibility matrix, then the joint displacement. In the joint displacements do not forget to include the initial joint displacement. So the initial joint displacements you can get from the contra gradient principle if the initial lack of fit is represented by D star initial at the element level, the effect that you get at the structure level is given by TF transpose. That is compatibility. That is the beauty of the compatibility relationship. Is it clear? So it is a very beautiful thing. You give me a statically determinate truss, let all the bars have different lengths, I do not care, but I should know how much different they are, whether they are longer or shorter by to what extent. So I have D star initial vector. If I pre-multiply D star initial vector with TF transpose, I get all the joint displacements in one go. In fact, that is a terrific transformation, but it works only for a statically determinate system, because if it is indeterminate then the flexibilities of the bars will have a role to play. This is independent of bar flexibility. It is a very interesting and powerful property. Let us demonstrate. So the first thing you have to do is to analyze the same truss to different unit loads one at a time. Apply F1 equal to 1, we have done this earlier, so I am going fast. Apply F2 equal to 1, apply F3 equal to 1, find out all the bar forces. Can I proceed? We did this earlier. Then you apply F4 equal to 1, apply F5 equal to 1 and fill up this matrix. Okay, so this is your TF matrix. Is it clear? The first column refers to the bar forces. Mind you, this F1 star, F2 star are nothing but N1, N2, right? So for example, let us look at this. This picture shows the results of analyzing it for F4 equal to 1. So that will help us fill up this column, and this is a very easy thing to analyze, because if you apply a vertical load here only bar 2 will get affected and that bar 2 will have a force of unity, right. So you can see bar 1 has force 0, bar 2 has unity, bar 3 has 0, bar 4 has 0, bar 5 has 0. Is this clear? So this matrix is a property of the structure. Even before you apply the loads you can generate that matrix, and it is applying one unit load at a time. The advantage of a matrix like this is that if you give me any load vector, I do not care what that load vector is. F1 could be minus 32.6, F2 could be plus 21.82, F3 could be anything. I get the answers in one shot. It is a linear transformation. In this particular problem you had only F3 having 100 kilonewton. I just multiply these two, I get directly the final answers. Is it clear? You might ask, why do I need to find out all this? I just need to solve for the single condition of 100 kilonewton, right, just one truss. That is what we do in normal structural analysis. But in matrix methods we say that is right, you can do only one problem that way. We are giving a solution which can do any problem. You change the loading, I can still do it in a jiffy by this matrix multiplication. Is it clear? So this step is straightforward, and the real power of this method comes when you deal with indeterminate structures. So I am just giving one example of demonstration for a statically determinate structure. Then you have the unassembled element flexibility matrix. You have got the flexibilities, just put them in a diagonal along the principal diagonal. You are familiar with that, right. So just this is F1, this is F2, this is F3, this is F4 and this is F5, that is your F star matrix, clear. 10 raised to minus 5, always avoid putting too many decimals inside your matrix, take it out, okay, otherwise you will run into errors. So keep the significant figures inside your matrix and keep out the 10 raised to minus 5 or plus 5 outside, right. Then you carry out this product, and if it is a big matrix then you do not do it manually, you do it through MATLAB or something, okay. You have TF, you have F star, you can do this product in one shot, you get F. There is no advantage in doing F star TF first and then TF transpose afterwards, because in this problem it does not make any difference. Somehow get the F matrix. Now the F matrix is a beautiful matrix. It says give me any load vector, and if I multiply that load vector, I pre-multiply that load vector with the flexibility matrix, I get all the joint displacements caused by direct actions, not by indirect actions. So give me any F1, F2, F3, F4, F5, if you have got the flexibility matrix you will get the joint displacement. So that is the next step, but before that let us find out the contribution of the the lack of fit. So this is what I said earlier, this is TF transpose and this is your initial lack of fit vector. If I just do this product I am getting the joint displacement. Now it so turns out that if the bar 4 is changing length, only this roller is going to move, okay, it is going to move inward, and the reason is simple, it is always good to get into the physics of the problem. Take the triangle ABC, the triangle ABC is not changing length, right, AB is 4 meters, BC is 3 meters, AC is 5 meters. So leave the triangle in peace, do not move it, right. Now CD is 4 meter, right, but with C as center and D as radius I can draw an arc and I still retain the 4 meter. So I move it inward so that BC is able to reduce length and get, so that is a physical meaning, you can do it by sheer geometry, and that is the reason why only one of these is non-zero, all the others are 0. That means the lack of fit in bar 4 is causing a movement of the joint D, all the others D1, D2, D3, D4 are 0. But the beauty about this particular transformation is, let all the bars have arbitrary lack of fit, minus 3 mm, plus 2 mm, I will get the final answer without worrying about the geometry just by pre-multiplying. It is a very powerful matrix, have you got it? So I have got the joint displacements caused by lack of fit. The final joint displacements is this plus what I got from the 100 kilonewton. So I just have to add it up, that is my answer, I have finished the problem. Is there anything left that is still missing? Well, if I really want the bar elongations, which normally nobody is interested in, I can find that also. So if individual deformations are required, D star I can get as D star initial plus F star, is it clear? But this is normally not required, you just need the joint displacements and you need the bar forces. If you want the support reactions, they are very easy to do through equilibrium. Shall we proceed? We now move to statically indeterminate structures, and you realize that you have a problem. What is the problem? What is the problem with statically indeterminate structures?
We have
with this equation.
Redundant.
What is the problem with the TF matrix?
It is not unique.
It is not unique. Multiple solutions are possible which are statically admissible. So it cannot be uniquely defined using equilibrium alone. Previously that TF was unique, you apply F1 equal to 1, the bar forces are unique, but you apply F1 equal to 1, you have an indeterminate structure, you do not know the answers, you got it. So we take advantage of the fact that a unique TF can be done. So what we do is we reduce that structure to a statically determinate structure and play our games with that primary structure. Is it clear? We did the same thing in stiffness method, but there is a big difference between stiffness method and flexibility method with regard to the primary structure. What is the big difference?
We have to choose a primary structure.
Here you have multiple choices possible. There you have to arrest the active degrees of freedom, right? Primary structure is a fully restrained structure. So that is the difference here. Okay. For a chosen primary statically determinate structure, the force transformation matrix is unique. Thus the TF matrix in a statically indeterminate structure depends on the choice of the redundants Fx. So let us say I am an examiner, I have solved the problem with my choice of Fx and the student used a different, I can't compare my solution with the student solution because we are dealing with different structures, primary structures, but I can check the final answer because my final bar forces must be the same. Is it clear? So that is the trick here. So what we do is we say that there are two force vectors, one is a load vector which I know and the other is the redundant force vector. So I have a primary structure, I can apply the redundants as loads on that primary structure. You are getting it? The difference between Fa and Fx is Fa is known, somebody tells me what the loads are on the structure, Fa is known, Fx is unknown, Fx is x1, x2, x3 depending on your redundancy. Is it clear? Now I have the primary structure is statically determinate. So corresponding to the active degrees of freedom, if 1, 2, 3, 4, 5, I can write a TF matrix. That TF matrix I call TFA matrix when I am dealing with Fa. When I am dealing with the redundant coordinates I call it TFX. So I can write my TF matrix as in a partition form like this, TFA when I am dealing with Fa and TFX when I am dealing with Fx. TFA and TFX are both uniquely defined. By applying unit loads I can generate TFA and TFX. So that is a property of the primary structure. So if I look at this vector, this is known, I can find this out, this is known, I can find it out, Fa will be given to me in the problem, Fx I do not know, but if somehow I can get Fx, I got the bar forces completely. Is this clear? Is this clear? So we have graduated from statically determinate structures to statically indeterminate structures. There is only one problem, someone has to tell me how to find out Fx because without that I can't solve it. Mind you, this equation does not give me F star, does not give me the bar forces because there is an unknown Fx hanging around, and that is because this equation is an equilibrium equation. Equilibrium alone cannot solve this problem, you need something more, you need compatibility, and this I have written for all the bars put together, but in general you can write it individually for different bars. Okay. This kind of form is useful in when you will see later in beams and frames when you have multiple degrees of freedom at the element level. Okay. Right. The unassembled element flexibility matrix is exactly what we did earlier, but for the primary structure which you have chosen. For the primary structure you have chosen, the primary structure will be different for different. Well, in this problem it may not make a difference, but in general your primary structure can be different. Okay. In this problem it may not make a difference. Okay. So structure flexibility matrix, the same transformation, but now this TF can be partitioned as TFA, TFX and so your F also, the flexibility matrix you can partition as FAA, FAX, FXA, FXX. The order of FXX will be dictated by the number of redundants, which is nothing but the degree of static indeterminacy. FXX and FAA will be square matrices. FAA and FXX will be square matrices, right, and FAX will be the transpose of FXA because of which principle? Because of Maxwell's reciprocal theorem, okay, that directly comes here. So, put together all your understanding. Remember when we dealt with the stiffness matrix, we also partitioned, but we partitioned as KAA and KAR and KRA and KRR, where R was for restrained coordinates. Here you replace R with X, X is redundant coordinates. So, you have active coordinates and redundant coordinates in flexibility method. In stiffness method you had active coordinates and restrained coordinates. Is it clear? X is redundant coordinate. Now what is the equation that you need to solve? It is a compatibility equation. Without this you cannot get the X. Now you have to satisfy compatibility at the active degrees of freedom and also at the redundant coordinates. So this is pretty simple to understand. dA dx is equal to dA initial dx initial in case you have some initial displacements like this lack of fit problem that we had, plus this flexibility matrix into what is sometimes referred to as the net load vector. Now sometimes you have some fixed end forces not in trusses, but remember the axial degree of axial element problem, you had some loads acting in the middle, we will do one problem of that kind, then you will have some fixed end forces which you have to bring in. So in such problems FFA and FFX will come, that is, so you can get your initial joint displacements through this transformation both at the active coordinates and at the redundant coordinates, and you get your net load vector FA minus FFA. Which of these two, you have two equations here, right, one related to dA and one related to dx, which of them do you need to solve to find the unknown redundants, the first or the second? The second one, right, the second one. So solve the second one, you get Fx, plug in that value of Fx, the redundants in the first equation, you get the joint displacements. Sometimes you may not be interested in the joint displacement, you just want to know the internal forces, then you do not even use the second equation, be happy with the first one. Is it clear? This is the flexibility method, it is quite simple, quite straightforward. The only thing is different people will have different solutions till the end, okay, the final solution should be the same, but the intermediate steps will be different. So the steps are, if you want to program it, input the structured data, generate the element properties, generate the structure flexibility matrix, compute Fx inverse because you have to invert Fxx in case you are dealing with a statically indeterminate problem, input the load data, compute the redundants, compute the element forces, compute the joint displacements. In statically indeterminate structures you can compute the element forces only at the end after you have got the redundants. Statically determinate structures you get it in the first shot itself because you have the TF matrix complete. Let us demonstrate with the same problem, okay. I brought in indeterminacy by adding one more element, a spring, okay, and the loading is the same 100 kilonewton, same lack of fit. Now this lack of fit, now you can see that earlier the roller could happily move inward by that amount, now the spring is not going to allow that. So it is going to cause some issues to the displacement field. We want to know all the answers in one shot using matrix method. Is it clear? Is the question clear? How do we proceed? Well, we will define the same global coordinates, but we will choose the force in that spring as the redundant. The spring can be treated as another axial element. We have done the same problem by one of those stiffness methods, okay. So F6 is x1, there is only the degree of static indeterminacy is 1 in this simple problem, and the compatibility requirement is dx is 0, d6 is 0. What does it really mean? In this instance it means that joint E does not move, but you could have used it as a cut in the spring, and then put the compatibility condition is there is no relative separation between the cut ends. Either interpretation is fine. Right now we have removed the support at E, and the reaction you get at E happens to be the force in the spring. Either interpretation is fine. Is it clear? Now I have got a 6th coordinate which was not there earlier, and I have a 6th element which was not there in the earlier problem. How do I proceed? Well, input load data is exactly the same, only thing I have fx, not fr, fx, which is x1, and the 6th element does not have any initial lack of fit. So I added one more element, and I added one more global coordinate, that is the only change, and my element flexibility is as given earlier. These numbers do not change, okay. But I have to now introduce the flexibility of the 6th element. Now the spring stiffness is given to me, I just invert it, I got the spring flexibility. Is it clear? So it is very simple. When you did the stiffness method, you retained the spring stiffness as it is, okay. Now what do we do? First write down your TF matrix, but now you have TFA and you have TFX. The TFA will be the same as the TF that we did earlier, because you had 5 elements, you have to add the 6th element, that is all. TFX we will find out. Find out your initial displacements as we did earlier. Primary structure you can find out uniquely. Generate the flexibility matrix, you have to add the 6th element. Generate the structure flexibility matrix, solve for the redundant, find the member forces, find the joint displacement. Absolutely straightforward, stepwise, okay. Let us do it step by step. Force transformation matrix, I just need to do one more case, that is I put F6 equal to 1, okay. If I put F6 equal to 1, I get these bar forces. The rest of it I have already done. This is what I did earlier, only thing I added a 6th row. Why did I add a 6th row? Because there is a spring which was not there earlier. Is it clear? There are 6 elements here. Is this clear to you? And my force vector, I add this unknown x1 as my 6th element. Any doubt? Ask. Okay, take this structure. If I apply F1 equal to 1, will these bar forces change here? Will I get any force in that spring? The spring is free here, by the way. You apply F1 equal to 1, will I get any force in that spring? Unless I pull the free end of the spring, even if I apply F5 equal to 1, that spring is just hanging loose there, nothing goes there. So do you agree that this is 0, 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 and it has a value when I apply F6 equal to 1. When I apply F6 equal to 1, what happens? Plus 1.
Plus 1.
It should be plus 1. You get tension in that spring. And that actually what happens, it is interesting, then it is like F5 equal to 1 for the rest of the spring, because I am pulling that end of the spring, it is as good as F5 equal to 1. So that is why this part of the vector is the same as this part of the vector. Agreed. So let us not go back, we know what we did earlier, we should write down the same vector. Then what do we do next? We write down the unassembled element flexibility matrix. Everything is the same except for the 6th element. We have computed the actual flexibility of that element, so that comes in as 12.5 into 10 raised to minus 5 meter per kilonewton. Then we do the same product, okay, and we get the stiffness matrix. If you compare this stiffness matrix to the previous one, what is common? Can you tell me? The previous one for the statically determined structure was a 5 by 5 matrix. Now you have a 6 by 6 matrix. What is common between that and this? FAA here is the same as the F earlier. Is it clear? So that is the only difference. So you will get the same matrix, okay, because you just have a 6th element. You have a 6th element. We will proceed. Then you need fxx, and you need to find the inverse of fxx, which is just 1 divided by that value, because it is a 1 by 1 matrix. Then you find the redundant by applying the compatibility equation, okay. A compatibility equation is dx is a null vector, solve it, you get some value minus 3.0593, okay. Mind you, in this solution we are also including the initial displacement. Earlier the forces were not affected by the lack of fit, but now the force is affected by the lack of fit because it is a statically indeterminate structure. Then what do you get? Find the member forces. Now that you got x1, you can get all the answers. Is it clear? Okay. And you have to find the joint displacements, and very easy, straightforward, exactly what we did earlier. But now you see you have joint displacements everywhere, it adds up. And incidentally we did the same problem by the stiffness method, you can just compare the final answers, you will find they match exactly. Is this clear? Statically indeterminate structures are not difficult, easy to do. Just want to raise one point. Here the compatibility equations depended on the choice of the redundant, and your flexibility matrix was a little complicated, right. But the actual structure did not have a redundant, the redundant was something you chose for your convenience. So what about the actual flexibility matrix of the structure? What will be the size of that? What is the size of the?
5 by 5.
It will be 5 by 5.
It will be 5 by 5.
Can you find out what that matrix is from these values? So that is interesting. It is just for your general understanding. You can have the flexibility matrix, which I am calling F bar, which does not depend on the choice of the redundant. You know, I could have chosen any bar force here as a redundant, but I do not need to. There are 5 active degrees of freedom in the actual structure, right, without, and I can write down this F bar matrix. Can you tell me how to generate this F bar from this flexibility matrix?
Keep F1 equal to 1 and use the compatibility condition, all those things, and get the bar for.
Can you write an equation? Can you write an equation? So it is a potential quiz question. Now you all wake up. How to write using whatever redundant you have chosen, can you write a flexibility matrix for this structure? So I will give you the answer, you can prove it, but I will leave the proof to you, okay. You can do it, because once you have got these, which means different students will have different submatrices here depending on their choice of redundants, but when they carry out this product everybody will be left with the same structure flexibility matrix. So the proof of this I will leave to you, but it is very interesting, okay. Last problem, let us quickly finish. We will do an axial system. Again I want to repeat, this is more for our learning, more for using it manually. Flexibility method is really not suited for a generalized solution for big problems, okay. So we have done this problem earlier. Now we will do both loading simultaneously. You have a direct action you have all those distributed loads acting, plus we have additional loading. Remember we did these two cases separately earlier, now we are doing it 2 in 1. The structure is statically indeterminate to the first degree, you can see, because if you remove one end it becomes determinate. Let us choose a support reaction at the right end D as a redundant x1 and model the two supports with rigid links. Okay, I am going to demonstrate here how you can also find support reactions bringing in additional members called rigid links. Okay, let me demonstrate that. The procedure is exactly the same, only thing here you have, it's a pity that you have to borrow a stiffness method idea to deal with distributed loads, because there is no other way you can handle it in a matrix framework. So you have to find out fixed end forces, which means going back to stiffness, borrowing that concept from stiffness method, and because if your fixed end forces are not constant in your element, you can't even do a matrix transformation, you have to do it manually. So those are the limitations of flexibility method. The rest of the procedure is exactly the same, no difference. Okay. Okay, now take a look. Okay, I have now introduced two elements here. Elements 1 and 2 were there in the original structure. I have introduced here elements 3 and 4, and I am calling them rigid links because they are short links, infinitely stiff. Okay, the idea is the force in that link is my support reaction. So I am able to access support reactions by converting them as internal forces in additional imaginary members, if I want to. Normally you would not do such things, you will just leave it in peace and find the internal force in that bar and then figure out what this support reaction is. But if you really want the matrix method to give you the support reaction just as the stiffness method did, this is one clever way of doing it. Introduce additional members whose internal forces will give you your support reactions. Okay. Now here my redundant is the force in at this end here, which I call x1, okay, which is a reaction in the other support, and it follows that the internal force in this element 3, okay, this internal force, it is positive if it is tensile. Do not you think it will give me the reaction pointing this way? This force, whatever, let us say I get 20 kilonewton, that internal force is my reaction Ra pointing to the left, then only I get tension. Let us say I get minus 20 kilonewton, that means Ra is pointing to the right. So I must be able to interpret the physical significance of the internal force in terms of the reaction that I really want, because actually there is no rigid link, I just created it. But here the force, the tension in the rigid link, which also happens to be the redundant because it has to satisfy equilibrium, that will give me my support reaction Rd pointing to the right because it is tension. Does it make sense? This is just for your general understanding, do not worry too much, do not do problems in the examination doing all this, but if you really want to, you can handle support reactions. I just wanted to demonstrate. So you are now having 4 elements, element 1, element 2, element 3 and element 4, okay, and all the 4 elements have only one degree of freedom, it is an axial degree, it refers to the elongation in that member and the corresponding force is the axial tension in that member. The 4 flexibilities are given. If you are dealing with a rigid link, what is the flexibility of the rigid link? 0, because the stiffness is infinity, 1 divided by infinity, and EA is given to you, so you can write down those values. Now you have to write down the force transformation matrix. Now write it down, okay, I am not going to spoon feed you, write down the force transformation matrix for this simple problem. What is the size of that matrix? TFA TX TFX? How many elements are there? 4, right? So you need 4 rows. How many columns are there? How many columns are there?
3.
So mind you, there are 4 global coordinates, 1, 2, 3 and 4. 1, 2, 3 belong to active coordinates, 4 belongs to redundant coordinates. So size of this vector is 4 by 1. The size of F star is 4 by 1 because there are 4 elements. So the size of this is 4 by 4. Give me that vector, give me that matrix 4 by 4. How do you get the answer? Apply F1 equal to 1. So it's very easy, it's like a chain. The clue is, if I pull the free end of the chain, all the forces will carry the same tension. But if I pull the front end here, only this will carry tension, these will just move along like rigid bodies. They won't have any forces, right? Can you fill up? All of you please fill up the TF matrix from first principles. TFA, TFX. It's nice to do new types of problems which you've never done before using very simple concepts. Have you finished? It will be just filled with ones and zeros, right? Have you all done it? Did you all get it? Raise your hands if you've got it. One solitary figure. Okay, let's do it together. To fill up this vector, I apply F1 equal to 1, which means I pull this end by 1. If I pull this by 1, which member alone will have axial tension? Number 3, yeah, you have to be careful about the numbering because this element 1, 2, this rigid link is 3. So the third only has 1, maybe you put it on top, you got it all wrong because your numbering, you should match your numbering. Okay. If you apply F2 equal to 1, the first 2 elements will have unit forces of 1 and 3. If you pull F3, 1, 2 and 3. If you pull F4, 1, 2, 3, 4. Does this make sense? Very simple. So it's really easy in a 1D system, it's a chain. Clear? Can we proceed? Supposing you didn't want to find the support reactions, it's a very simple problem, 2 by 2. Okay, now this part you have to borrow bodily from reduced element stiffness method, okay, or stiffness method, because there also you need this. So remember, we've done this, you have to find the fixed end forces, and after you've done this you have to figure out what the fixed end force vector is. So you look at these results and then manually you have to figure out what F1 to F is, what F2 F is, F3 F and what F4 F is. So look at this structure, F1 F will be the force in this coordinate. So this is 1, 2, 3, 4. So F1 will be minus 20, you can see this direction. F2 will be minus 40, F3 will be minus 10 because it is pointing this way. See, F1 is pointing to the right, F2 to the right, F3 to the right, and F4 is 0. Is it clear? From this figure, the top figure alone, pick up F1, pick up F2, pick up F3, F4 is outside. Any doubts on this? This has to be manually picked up. In addition, you must keep in store all these axial force distributions and the axial displacement distribution. Any doubts on this? We have done the analysis earlier, we are just picking up manually F1, F2, F3. Any doubts? Shall I explain once more or is it clear? Clear, good. Then you need to find the net load vector. Remember, in the original problem you had F2 equal to 40 kilonewton, but now you have the fixed end force vector which you have to oppose for your equivalent joint loads. Remember, you have to put in the minus sign, and then you get the resultant net load vector. What do you do next? What do you do next? This is your, if only you knew x1 you could get the forces, right? This is your force transformation. How to find x1? Compatibility. What is compatibility?
Dx equal to 0.
Well, before that there is an indirect loading, do not jump. The indirect loading was you had a temperature change in the two elements, so it is like a lack of fit. In the primary structure they will be freely elongate. This is the elongation you get. What do you need to do? You have to find the effect they have at the joints by doing the transpose. So, of the two support displacements prescribed, 2 mm and 1 mm, the one at the left support is a non-redundant coordinate. It can be visualized as an initial elongation in the rigid element 3. Do you understand? Remember, you had two elements, you had an extra element you put 3 and 4. Support, the first one is, okay, this is temperature loading, but you had a support movement also. The temperature loading you can handle directly, but the two supports were moving. Remember, A and D were moving. A moved to the right by 2 mm. It is like the rigid link 3 had an elongation, a lack of fit of 3 mm. Are you getting it? The rigid element 3 had a lack of fit. It was too long by 3 mm. It is as good as the support moving 3 mm. Is it clear? But the second one, this is a tricky one, which corresponds to a redundant coordinate, because that fourth rigid link, the right end of it is your redundant location. So that will go to dx directly. So there is a little catch in this, it is a beautiful problem. Dx is d4 is 0.001. So if you want to write down the compatibility equations, you can convert these to the joint locations doing this transformation. Please go through this example very carefully because it has got all kinds of complication in it, and you have to write the
where D3 initial is 0.002.
You see, in the initial primary structure, what are the changes you get at the element level? Firstly, element 1 has, due to the temperature increase, is increasing its length by 8.8 mm. Element 2 is increasing by 6.6 mm. Element 3 is
given
is increased by 2 mm. Element 4, in the primary structure that point is free to move, it is a redundant coordinate. So you have to accommodate it in dx in the compatibility equation, not in the member elongation. We have done similar problems in method of consistent deformation. Remember when we did the formulation, you had delta 1L, delta D. So you had to know which to put in the delta D column and which to put in the dx column. Similar situation here. In the dx column, the redundant location you put directly the value, in the non-redundant location you put the other value. So if you understood that, generate the element flexibility matrix. Okay, you have the TF matrix, you have the F star matrix because all the elements, these F3 and F4 are 0, so the bottom rows are 0, and find out F matrix by doing this product. Okay, the procedure is clear to you. Any doubts on this? Just pre-multiply, post-multiply, and pick out Fxx. Fxx is always at the lower right hand corner. Always Fxx is located at the lower right hand corner, and this is your compatibility equation. Remember the dx here, the final solution is 0.001 because the right support moves by 0.001. So your primary structure, that is your dx, and this is your complete equation. So the formulation of this problem is very interesting. If you make a mistake in the formulation, your solutions will be wrong. So you carry this out, solve for your redundant, you will find it is 50.5 kilonewton, find your member forces, you have got the results. Okay. If you add up the two solutions which we did in the stiffness method, you will get this. So it is a final check on this. So are you comfortable with flexibility method? In your examination, I will ask you at the most only trusses, because whenever you have intermediate loading and all that, flexibility method is not good. So this you just read and put aside, do not break your head too much over this, but trusses you should handle any flexibility problem. Is it clear? Two types of problems, direct loading, second is lack of fit or temperature loading. Can you handle those two? Indeterminate structure, plus you have an assignment problem which you can do. This is a little more difficult, and you need not find support reaction using rigid links unless you are forced to, like here. Here there was another need because the support was moving and there was no other way you could handle it. Is it clear? You can find the support reactions also, find the axial displacements and get your final solution. Is it clear? So we have completed 1D structures, space frames, we have done conventional stiffness method, reduced element stiffness method and flexibility method. Tomorrow we will work with beams and grids, that will last another 6 lectures. Thank you.